fictitious example here is that, on rainy days it's quite humid, you don't sell a lot of ice cream, and on sunny days it's not very humid, but you do sell a lot of ice cream. So you can sort of hypothetically imagine that these data would start populating different areas of the space depending on the class. So here we're looking at two classes, right? The class or category of day that it's rainy, and the class or category of day that it's sunny. Yeah? Everyone happy? So I'm throwing some terminology. We've got two classes here, the sunny class, the rainy class. We've got training data here, and the data, we have features that are being measured about it. We've got two features we're measuring for every day, the humidity and the ice cream sales, and that gives us our feature space. Everyone happy with that? Okay. Features. So the features then are the things that we can observe about the data. Right. Now, in our very simple machine learning example here, what we're going to do is train a model for these 2 days, and the simple way that we're going to train this model is we're going to average together the features for each category. So for our rainy days, we're going to work out for those 50 days what the average humidity was and what the average number of ice cream sales are, and that's going to give us a point in this space, which is just the average of those two-dimensional vectors, and we're going to call that our model. Okay, that's our thing that we think represents what it is to be a rainy day. For the sunny day, we're going to do the same. So now we've trained up 2 different models just by averaging their features together. Yeah, the model for the rainy class or category, I told you those terms are interchangeable, and the model for the sunny class. Everyone following? Yeah? Okay. Now, let's suppose now, having trained my system, I go out and in fact, let's not go out. Let's just pretend I stand in this room and I ask someone on the phone, how many ice creams did you sell today? How humid is it today? And then, what I want to do is, based on those 2 features that have been measured about this new unseen day that wasn't part of my training data, I want to make a decision about whether today, on my test day, it is a sunny day or a rainy day. So how do I do that? Well, what I'm going to do is measure how close that test day is, which remember is also a point in our feature space because we measured those 2 features about it. I'm going to measure how close it is to my sunny model and my rainy model. And the model that it's closest to is going to be what day it is. So in this example, it's a sunny day. Yeah? So the final thing then that I need in order to build my classifier, I've talked about how we trained it. We trained those 2 models. The final thing we need then is a way to measure the distance in that feature space between a test point, having measured the features for that test point, and the models. Everyone follow? Okay. Right. The last piece of terminology that I want to introduce to you today, well, it might be a bit of a lie, there might be some more later, but in this slide at least, is something called the decision boundary. Decision boundary is nothing, we never calculate the decision boundary, it's just a conceptual thing we talk about in machine learning. Okay? As you can see in this space, where we've got this very simple 2-dimensional space, and we have the models represented just as these points in the space, which are the averages of those features, you can see there is a region of this space where anywhere this test point lands, it will be closer to the sunny model than it is to the rainy model. Yeah? And there'll be another region where the opposite is true. And those regions of the space are separated by something that we call the decision boundary. Okay? It's just like a hypothetical line through the space, a bit like an event horizon for a black hole, right? It doesn't actually exist as a physical barrier, it's just a mathematical point beyond which, if you go too far, you get sucked into the black hole. Same sort of idea with the decision boundary, right? It's a sort of a mathematical boundary beyond which you go beyond it, you're in that class. Yeah? Okay. So, how do we measure this distance? Well, it turns out in machine learning there are lots of ways to measure distance between 2 points in a space. Some of the most common ways that we do it are to calculate what's called the Manhattan or city block distance. Oh no, hang on, we're not going to do that one next. We're doing the Euclidean distance. Okay, so actually one common way is to calculate something called the Euclidean distance, which is just the direct, but let's suppose f1 plus f2. Okay, everyone happy with that? So, in the weather example, quick quiz, what were the categories of classes? sunny and rainy. Oh, okay. What was the feature space? Ice creams and humidity. What were the class models calculated via? How do we calculate the models? We average the features for each class. Notice we average the features for each class independently, so we built a model for each class. That's always the way we always build a model for each class in classification. Although, as we'll see later, there are better ways to build models than just averaging the features together. How do we measure the distance? Yeah, in that example, it was the L2 norm. What was the training set? Okay, it was 100 samples, 50 of each category, rainy and sunny. And what was the decision boundary? Well, because we had two classes, because we were measuring the L2 norm, it was just a linear decision boundary through the space. Yeah? Okay, great. Anyone got any questions on that example there I gave? All right. Yeah, just a one. Told you there was more terminology. Another piece of terminology here. If we're building a classifier between just two classes, in this case sunny and rainy, we have a special word for that. Sometimes we call it a binary classifier, sometimes we call it a dichotomizer. Okay. Okay, well let's look at it. Oh yeah. 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 No, you wouldn't. So, okay. So in this, the question was, what if I only knew one feature and not two for a day? In this example, no, you couldn't. You need to know everything about a day. There are more sophisticated machine learning models where you can have like unknown features. They're actually quite rare. We don't cover them on this course. Okay. It's a good question though, thank you. Okay, let's look at another example now. Let's suppose that I'm in a world 5 years ago when we were still renting DVDs and not just streaming stuff on Netflix. Okay, and I wanted to make a movie recommendation system for my DVD rental store. Okay, now in this example, what we're going to have is customers that go watch films, and then they're going to rate the films they've watched on a scale. So that customer's preferences have been represented as a point in the space. We can. So, in summary, supervised classification then is this problem of learning models for each category or class of your training data, yeah, and calculating, basically given a test point, which of those models the test point is closest to. That is performing classification. So there are several design challenges we have to think about as engineers when we're building these systems. Importantly, we have to decide what the feature space is. In other words, what things are we going to measure about the world in order to train and test the system? We need to think about how to model the categories. So far, I've just showed you the simplest way of how to go about modeling categories, which is just average their features. But as we'll see later, we can do better. And we also need to think a little bit about how we're going to calculate the distance between them. Okay. Right now, it may seem like, well, why would you ever do anything other than calculate the direct distance, Euclidean distance? But actually, it turns out with machine learning that by varying this distance measure, sometimes you can get better performance by computing different kind of distance. And it can also be more efficient to calculate the L1 distance. Right, so finally then, let's get back to computer vision and see how we can apply these concepts to build a classifier. And this time we're going to build a classifier that tells us whether a pixel in an image is part of the sky or not. Okay, so our classification problem is going to be visit every pixel in turn in the image, and for every pixel make a decision, sky or not sky. And we're going to use this to then pick out the region of the image that contains the sky. So what do you think would be a useful thing to measure about a pixel in order to determine if it's part of the blue sky or not? The colour. Brilliant. Okay. And remembering last week, how do we represent colour typically in an image? RGB. So for every pixel, we measure the amount of red, green, and blue in that pixel. Yeah? So our feature space then is a three-dimensional feature space where the features are red, green, and blue. And our classes in our system are sky or not sky. Okay. So let's suppose then that we take from some different image a patch of blue sky as training data for our system. And we're going to measure the RGB value of every pixel in this training data. So we have as many training samples as we have pixels in this little patch of blue sky training data. Okay? We can therefore represent those pixels, those training data, as points in our three-dimensional feature space. Yeah? And what we're going to do is use our simple technique that we learned of just averaging the features together to create a model of that training data. So this cross here is our model, which has been calculated by calculating the average red, average green, and average blue value of the pixels in our training data set. So this is our model we're going to use to classify these unseen pixels in this new image here, okay, one at a time. Yeah? So what we're going to do is take a pixel in that image, and we're going to, let's suppose we take this pixel here, that is going to have some RGB value, yeah? And therefore, those three features are going to enable us to plot its position in this three-dimensional feature space. Let's say it's here, okay? Now, it should be clear that in this example, a bit of blue sky here is going to be closer to the model that we've trained on the blue sky. It's going to have similar colour to that training data than, say, a pixel that's been sampled from a non-sky region, like, for example, this sort of sandy rock-coloured region. So points that are resembling sky are going to be closer to this model than points that are not sky. Yeah? And we can measure how close they are using our Euclidean distance. And remember, we're working in three-dimensional feature space now, so we have these three elements in our equation here, these three terms. Yeah? Yes. Brilliant. Yeah, thank you for that. I'm coming to that. That's an excellent point. So in this example, actually, we've just trained one class, but we're trying to make a decision between sky and not sky. So what do? We've only trained one class, not two. The reason that I've tackled the problem in this way is because whilst sky is easy to define as a class, the space of not something is a lot harder to define, particularly using a simple model like this. So what we're going to do here is do what we call threshold the distance. Okay? So remember, our distance is given to us by this expression d. So what we're going to say is that when d is greater than a certain distance away, that point is not sky, and when it's closer to the model, when a d is less than a certain threshold, then it is sky. Okay? And if you think about it, when we threshold d, what that's doing is creating a decision boundary in our space that is a sphere. Yeah? Everything within the sphere is sky, and everything outside the sphere is not sky. So, assuming we can choose that threshold correctly, this point will fall within the decision boundary, and this point here from the sandy-coloured rock will fall outside the decision boundary. So, indeed, as you've just said, we could have done something like train two models, one for sky and not sky pixels, but because we're trying to train a model for what we sometimes refer to as the null category, the category of things that are not in our data, sometimes it's better if we have this problem of something or not something, just to train a single model and calculate a threshold on the distance from that model. Yeah? Everyone happy with that? Yeah? Great question. That is the question. How do we choose a threshold? Thank you very much for asking. Okay, so how do we choose the threshold? Well, it's important that we ask that question because the different value threshold that we pick will have a dramatic effect on the performance of our system. if I take my image and I calculate that Euclidean distance of every pixel in that test image from the model I built, what I'm going to get is something like this. And what I've done here is I've visualized every pixel by shading the pixel with a grey value. The brighter the value, the further that pixel is from the model. So you can see that things that are not sky are much brighter in this image. Now, if I were to set my threshold to be at a certain value, now in this example what I've actually done is I've taken my R, G and B values, and instead of having them in the range 0 to 255, as we discussed last week they commonly would be, I've just normalised them to be in the range 0 to 1. Okay, so the value that I've chosen for a threshold here is 0.2 on my distance, yeah, my Euclidean distance. Now what that's giving me is decisions that are correct for this non-sky regions, but it's also giving me regions of sky that have been misclassified as being sky, as being not sky, sorry. Okay, so this is an example of a false negative in our system. It's something that's been identified as being not sky, it's a negative falsely, yeah, incorrectly. If I set my threshold to 0.3, then actually I've got the opposite problem. What I've got here is false positives, okay? Because what I've got here is regions that have been identified as sky when they're not sky, okay? So clearly there's a balancing act going on here in terms of choosing the correct threshold. What I would like is to choose a threshold that gives me something like this. And this is my ground truth. So what I've done here is I've loaded up this image into Photoshop. Other products are available. And what I've done is I've drawn basically a shape in white around that object. And I've created this black and white image here. It has a special name actually. It's called a binary mask. Okay, it's an image that's just got black and white in and nothing in between. And this is a mask that shows basically where the object is, and therefore it's defining a ground truth for what is sky and what is not sky. Everyone happy with that? So what I would like then, to define how good my threshold is, if I pick a threshold, you know, the best threshold I can possibly pick would be the threshold that gives me a classification decision that is closest to my ground truth. Yeah? Okay, so what I'm saying when I want to measure how close my classification output is to my ground truth, what I'm saying is I want to evaluate my classifier. So thinking back a few slides ago, how do I do that? I build a confusion matrix. Okay, so again, with the confusion matrix, what we've got here is our ground truth, which is positive or negative for sky, and then I've got my outcome for my classifier, which is again positive or negative for sky. And what I'm going to do is look at all the examples where I've got true positives. So that is, in this example for t equals 0.3 here, I'm looking for all the examples where basically my ground truth says it's sky, but my output for my classifiers also said it's sky. Okay, so in that case, I've actually I've got 100% accuracy there for my positive class. But look, for my negative class, for my classification of not sky, I've got a low accuracy. And I've also got values in my off-diagonal as well. Okay, so this then gives me my basis for calculating how accurate my system is. I can calculate a mean average precision by averaging down my diagonal. So that will be one way to quantify in a single number how good my classifier is performing at t equals 0.3. But as we got from the question a moment ago, what I'd really like to do is use this to tune my threshold to pick the optimal threshold value. So a way we commonly do this in computer vision is to use a curve we call the ROC curve, or it stands for receiver operator characteristic, because this stuff used to be used in radio, but we use it for computer vision as well. And what we're going to do is plot on here for a value of t, for example, for this threshold here, I've chosen 0.1, so it's got a massive amount of false negatives here. Okay, what I'm going to do is calculate that false positive value and the true positive value, and plot that as a point on the two-dimensional axes here. So this axis here says false positive rate. This is the percentage of false positives. This here is the percentage of true positives. So every value that I choose for my threshold is going to give me a point in this space. So what I'm going to do is just choose every possible value of threshold from 0 all the way up to, you know, effectively infinity. Yeah, and that's going to trace out a bunch of points in my space. And what I'd like to do is find the point in my space that is closest to this top left corner, where my true positive rate is 100% and my false positive rate is 0. Yeah. Now, in this example, clearly no value of threshold has given me that. But I have got a value here, which is closer to that corner, which turns out to be 0.24, which gives me this image here, which is the best output I can hope for, the best threshold I can choose, given the model that I've trained. So in an experimental setting, if I were choosing a threshold, what I would do is run a process like this, where I plot an ROC curve for an image, or maybe I average it for a set of images, and I produce this plot, and I look to see which value of threshold gives me the optimum score, okay, position of my ROC curve. And that is going to be the threshold that I choose. Yeah? Yeah, you plot it manually. Well, I mean, I say manually, you'd write a program that iterates through the different threshold values and does this computation for you, and then plots the curve, and then you'd look at it and pick the right threshold value. Yeah? So, the big question then is, can we improve on this? I've just told you this is the best we can do. It doesn't look great, does it? We've still got a little bit of sort of misclassification going on here. Well, how could we improve on this performance? Maybe we could choose different features to measure about the pixel, but probably we couldn't really, because a pixel's only got R, G, and B. You know, we could start looking at patches of images and look at the texture maybe. That would be another way of doing it. But the best way that we can improve on this performance would be to use a more sophisticated kind of model. So right now, our model, remember, we're just building by just averaging the red, green, and blue values. But it turns out that we can build something, the model's not just the average of that training distribution, but also its shape, yeah, what we call the covariance of that training distribution. And to do that, we build something called an eigenmodel, and that's what we're going to look at next time, in fact, for the next 2 lectures. So then in the session today, we've just started off really talking about machine learning. We've looked at what classification is, and we've looked at supervised and unsupervised versions of it. And I've introduced a lot of terminology to you. We've talked about under and overfitting. We've looked at how we train and evaluate classification systems. And all these terms I've introduced to you here, things like feature space, decision boundary, distance function. We looked at different ways of measuring distance, and we looked at a really basic solution to machine learning problems, to classification problems, which is to average the features in your training set. But next time, we're going to look at a more sophisticated model, the eigenmodel, as a way of solving these supervised classification problems. Okay, thanks very much, and see you tomorrow.